Hey there. In this clip I want to talk to you about the very basics of indexing. So, why are we interested in indexing? Because indexing is a very easy way to improve the performance of your database under a set of fairly common circumstances. So the point of indexing is improving database performance. What is an index? An index is a structure that exists independent of the data in your table that improves the query optimizer's ability to execute your query quickly. While it's not exactly the same, an excellent analogy for understanding the basic functionality of a MySQL index is the index that you find in the back of, for example, a textbook. And so, imagine that you needed to find in your textbook every instance of a particular word. Let's say if you had a database textbook, you had to find every instance of the word concatenate. Well, you have two options. Without the index, your only option is start at the first word in the textbook, read every word from top to bottom, left to right, until you've reached the end of the textbook, making a note of each time that you come across the term concatenation. That takes, as you could well imagine, a very long time. And as you likely from your own textbook use know, there is typically an alternative. Provided that the term in question is available in the back of the book index, you can jump directly to the index, go alphabetically through the index until you get the C's, find the CO's, find the word concatenate or concatenation, I can't remember which one I said, and then find in the index every instance of concatenation and a direct pointer to where you can find it in the textbook. Obviously, that saves an inordinate amount of time in terms of tracking down a particular concept or terminology in a text. And the basics, although the execution is different, the basic purpose is exactly the same with database indexing, and the performance improvements stand to be equally significant as well. Okay, so let's take a quick look at how indexing works. So here we have, let me get to drawing here. Here we have an unindexed table. Okay, and basically what you have is an unordered lumping of data records. And we know from our previous studies that ordering can't matter in a database table. You know, whether a particular record is first or last or 17th can't really make any difference to us. However, in terms of the performance of the table, that ordering can. And so what we have within, and more on that in a moment when we actually talk about the index, but what we have here with the unindexed table is basically the same situation as a textbook without a back of the book index. To find a particular value, say for company number, you need to say we're looking for every instance of company number with company number equals 14. We got to go from the first to the second all the way down and say, okay, here's one and here's one, and those are the only two. And obviously that's not that big a deal with a table as short as this, but imagine that we had a table with millions of records, or imagine further that we had a table of thousands of records being joined in a query to another table of thousands of records, being joined in turn to another table of thousands of records, and then we are dealing with comparisons in the billions, literally, and performance can be impacted. So we want to avoid the situation of having to read in series from the first record straight through to the last, to scan, in other words. We want to search instead of scan. We want increased efficiency, and we can get that with the inclusion of an index. And so here we are with our index provided. It's an index on company number, comp no, and what it is an ordered arrangement of all the instances of company number from smallest to largest, together with a pointer to where those instances occur. So together with this 10, just like a back of the book index, we have a pointer to the underlying data, i.e. the text of the books, or in this case, the instances in the database. So we have 10 here, 10 pointing to here, and 10 pointing down here, and so on. We have 11 right up here, and 11 right here, and 14 here, and I won't do all of these. You get the picture. So we have each of the instances and a pointer to their underlying data in this table. And so this improves in performance because instead of having to look top to bottom, we can say, okay, I am looking for company number, every instance of company number 11. Okay, and so I can say, instead of scanning the index, I can do more sophisticated searching using binary trees or other data structures that we will not talk about, but they function similar to guessing game, where if you have to guess a number from between 0 and 100, your first guess would be 50 if you're able to be told whether your guess is higher or lower. And if you guessed 50 and you were told that that guess was too low, then you would guess halfway between 50 and the maximum value of 100, which is 75, and that sort of thing, which is beyond the scope of this course, but hopefully you get the picture a little bit. In any case, you can say, all right, so here's my value of 11 that I'm looking for. Here's one instance of it, go down again. Okay, we're still at 11. Here's another instance of it, go down again. Oh, we're on to 14. We have extended the bounds, gone above 11. I must have therefore located every instance of 11, and I can stop screwing around. I know I am done with this search because the index has done its job. Now, one thing you may be wondering to yourself is, this makes a lot of sense, and I get it, but why do we need this to be a separate structure? Why don't we just order the underlying data in descending order, or in ascending order rather, from the lowest comp number to the highest? Well, that just basically, why don't we order this column instead of creating this index? That works fine with an asterisk, as long as you only want one attribute indexed. It's oftentimes imperative that you index multiple attributes. You know, if you also wanted to index the add number, then which is it going to be? You could sort by this column, or you could sort by this column, but you can't sort by both. Where we could certainly create a separate index with a separate set of pointers over here, and that would be fine. So that's one of the main reasons that we like to have a separate structure to keep the ordering, because it allows us to order on multiple attributes. The other thing is this, well, this in terms of the number of attributes is just 1, 2, 3. It's very brief, and each of the attributes is fairly short. In reality, this could go on for many attributes, some of which are binary large objects or large chunks of text or Lord knows what all. And managing especially if this table is changing a lot, if it's volatile, managing the constant reordering is more time consuming and more difficult if you have all that other junk to have to rearrange as well. Whereas the index while it's not costless to have to constantly update the index to reflect the changing nature of the underlying data, it's much easier than constantly having to reorder the underlying data itself. So that would be a cost as well. But really the biggie is the fact that you can only pick one and only one attribute if you were to order the underlying data. So instead, we go with index. So I think that's the basics in terms of conceptual ideas about indexing. I want to talk in a follow-on about when it makes sense and when it specifically does not make sense to index. I want to talk about full text indexing, which is slightly different and more Google-like. And I want to show you the syntax involved in indexing. But for now, that's the very basics. Study hard, and I will see you online.